There's a Jupiter-sized planet 1,200 light-years away called WASP-12b. It orbits so close to its star you could see surface details with your naked eye. Mercury is the closest planet to our Sun. WASP-12b orbits even closer at d.02 astronomical units. You could fit over 3,000 Earth-Sun distances between it and its star. One orbit takes 26 hours at 600 kilometers per second, over 1.3 million miles per hour. It's in constant freefall. The day side reaches 2,500 Kelvin, hot enough to vaporize lead and sink hotter than many star surfaces. Tidal forces stretch the planet into an elongated egg shape. Gravity at its surface is so much stronger than at its core that the whole world is being pulled apart. Thousands of similar ultra-hot Jupiters exist. WASP-12b sits at the far edge of that population. At this distance and temperature, the question isn't whether WASP-12b survives. It doesn't. The question is how long it has left. The heat boils its atmosphere. Hydrogen and helium bleed into space, millions of tons per second, in a visible tail stretching millions of kilometers. Spectroscopy reveals the fingerprint of hydrogen and helium vanishing into the void. We're watching it happen right now. Every 26 hours, another orbit. With each one, it loses more of itself. So the question becomes, what stops this from happening to planets in our solar system? Tidal forces don't just stretch WASP-12b from the outside. They work on gravity gradients. The near side of the planet feels a much stronger pull from the star than the far side does. That difference in pull stretches the whole planet. Imagine bending a wire back and forth. The metal heats up from friction. WASP-12b flexes every time it orbits. Each bend converts mechanical stress into heat. The core and mantle compress, deform, and release energy. This isn't a one-time event. It happens every 26 hours, every single orbit. The core reaches temperatures that rival stellar fusion environments. Not quite hot enough to fuse hydrogen, but close. No rock could survive in that state for long. That interior heat has to go somewhere. Convection currents rise from the core through the mantle and into the atmosphere, moving energy upward. Heat drives convection currents in the atmosphere itself. Convection doesn't distribute energy evenly. It channels it into focused jets, where material escapes fastest. Meanwhile, the star itself is blasting outward. Every star throws off a stream of charged particles, the stellar wind. It flows across the star system constantly. Stellar wind alone would strip away atmosphere slowly. Tidal heating alone would boil it away. Together, they create something far more violent than either force alone could manage. WASP-12b sheds enough atmosphere every second to equal the mass of an Olympic swimming pool filled to the brim. That's the loss rate. That material doesn't just vanish. It forms a visible tail, trailing behind the planet, a comet tail light years across. But how do astronomers see it from billions of kilometers away? We can't see WASP-12b's tail directly, but we see it in starlight. As the planet orbits in front of its star, light travels through its escaping atmosphere. The hydrogen and helium absorb specific wavelengths, fingerprints. Each element writes its own signature into the starlight. During the transit, the star appears slightly dimmer because the atmosphere absorbs just enough light to leave a detectable dip in brightness. This is transmission spectroscopy, the method that discovered the first Earth-sized exoplanet candidates in potentially habitable zones. We measure what's absorbed when worlds pass in front of their stars. But WASP-12b spectroscopy shows something unusual. The hydrogen absorption extends millions of kilometers beyond the planet's edge. The tail is wider than the entire planet. Hubble's ultraviolet spectrograph captured this directly. The absorption signatures are stark and unmistakable. This is observation, not inference. We're watching the atmosphere escape in real time. Stellar wind and radiation pressure push the tail backward. The planet's own gravity can no longer hold the escaping atmosphere. The spectroscopy reveals more than hydrogen and helium. Oxygen and carbon signatures appear in the tail selective atmospheric removal driven by heat and gravity. This happens every 26 hours. Every orbit of WASP-12b, the same patterns repeat. An ongoing process we can track. If WASP-12b is dying this way, how many others are losing atmosphere right now? Every ultra-hot Jupiter near its star could be in the same spiral. The tail itself is staggering. It stretches 5 million kilometers from the planet, farther than the distance from Earth to the Sun. Visible light cannot show this. The tail only glows under ultraviolet. Hubble's UV spectrograph reveals it as a clear, wide absorption feature, larger than the planet itself. The numbers are what make it real. The atmosphere is escaping at roughly 100 billion tons per second. That's enough to lose Earth's entire atmosphere in less than a day. The process is not slow, it's catastrophic. At this rate, WASP-12b will shed its entire hydrogen and helium envelope in 50 million years. 50 million years is nothing. What remains when the gas is gone? A rocky core, dense, exposed, still baked by the star's radiation. Astronomers call these worlds Chthonian planets. Terrestrial cores left behind after their atmospheres boil away completely. We've already found them, strict cores in tight orbits where gas giants should exist. This is not speculation. We observe it directly. WASP-12b itself may not survive even that long. Tidal forces may tear the core to pieces before the atmosphere finishes escaping. The timescale could be 10 million years instead of 50. And WASP-12b is not alone. Thousands of known exoplanets are undergoing this same process right now, losing mass, approaching their end, in systems we can observe from Earth. WASP-12b didn't start at the edge. It formed farther out, in a cooler region where gas giants are born. Then it moved. Planetary migration happens during a star system's infancy. Gravity from the disk of material shuffles planets inward or outward. Sometimes inward wins. A single close-orbiting gas giant proves migration was real. It tells us the solar system wasn't born as we see it now. Our own Jupiter and Saturn migrated inward, then outward, reshaping the orbits of rocky planets and flinging asteroids. WASP-12b is a fossil from that violent reshuffling. We found thousands of these close-orbiting gas giants. Each one is a message from its star system's past, written in its current position. What WASP-12b reveals about hydrogen and helium loss, which elements survive close orbits and which don't, shows us where life could persist. We now know that stable atmospheres require specific orbital distances. Too close and you lose everything. Farther out, worlds keep what they need. Earth orbits at a distance where our atmosphere could survive billions of years. That distance is not special, it's survivable. Some worlds form in the danger zone, doomed from the start. WASP-12b is one of them. But not all close-orbiting planets die, not yet. By watching a planet die, we understand why they live. And we're forced to ask, how stable is ours?